In this video, I'll be explaining the intermediate value theorem, what it means, and why it's useful. The intermediate value theorem says that if you have a closed interval, a to b, and some function f, which is continuous on that interval, then for any number L, which is between f of a and f of b, there must be a c in between a and b such that f of c equals L. But what does this mean? Think of it this way. Imagine you're in Washington Square Park and you want to get to NYU Tandon at the Metrotech Center. At some point, unless you teleport, you're going to have to cross a body of water. Whether by bridge or tunnel or even flying, you must at some point in time pass over, through, or under a body of water. This is what the intermediate value theorem is saying. Think of your starting point and ending points as f of a and f of b, and the East River as L. As long as your path from Washington Square to the Metrotech Center is continuous, i.e. no teleporting, you're going to have to cross a body of water, L, somewhere along the way. Another way of phrasing the theorem is to say, if a continuous function is equal to one y value at the beginning of an interval and another y value at the end of the interval, then the function must also be equal to every value in between those two y values at some point on that interval. Let's try an example problem. Does the function f of x, which equals 2x cubed minus 5x squared minus 10x plus 5, have any real roots? What this type of problem is asking you to do is find the interval where f of a and f of b are on either side of the x-axis and L is equal to 0. Let's try some x values out. If we let x equal -1, then f of -1 is 2 times -1 cubed minus 5 times -1 squared minus 10 times -1 plus 5, which becomes -2 minus 5 plus 10 plus 5, which equals 8. So now that we've found one x value, where our y value corresponding to it is above the x-axis, if we can find another x value where the y value is below the x-axis, we will have found a root somewhere in between there. So let's keep trying some more x values. If x is 0, then f of 0 is equal to 2 times 0 cubed minus 5 times 0 squared minus 10 times 0 plus 5, which becomes 0 minus 0 minus 0 plus 5, which equals 5. We're still above the x-axis, so we're going to need to keep going. Let's try if x is equal to 1. Then f of 1 is equal to 2 times 1 cubed minus 5 times 1 squared minus 10 times 1 plus 5, which becomes 2 minus 5 minus 10 plus 5, which is equal to minus 8. So now that we've found one x value, 0, which corresponds to a y value above the x-axis, or is positive, and another x value, 1, which corresponds to a y value which is below the x-axis, or negative, we know that somewhere in between 0 and 1, we must cross the x-axis. Or, if we let our a equal 0, and we let b equal 1, then we know that somewhere on that interval 0 to 1, there is some x value such that f of x equals 0. So, this theorem is useful if we want to show the function hits a certain value even if we don't know exactly where. In this example, all I could say is that there is a root between 0 and 1, but I wasn't able to say exactly what the x value is that corresponds to 0. Usually the value we use for L is 0, because 0 and roots in general become very important in calculus.